Hello everyone, my name is Jan, and today I'm here to present to you my work called GROut, and it is a way to transfer scale your workload to overcome unified virtual memory over subscription slowdowns. So, the general topic that we will be talking about today are GPUs. GPUs are a widely adopted hardware accelerator. You find them lacking the training and inference of large language model. They have become the de facto standard hardware accelerator. To program GPUs, you have two main approaches. The first one is the traditional approach where you have distinct memory regions for the distinct devices and your processor or your main memory. These require manual memory management, so you need to issue movements, data synchronization, asynchronous computation and transfer overlap. And if you want to handle large data sets, you need to implement some sort of batching mechanism in order to process them. On the other side, you have unified virtual memory, which is a simplified way to program GPUs that allows you to have a single uniform address space where you can use a single pointer shared among the devices and the CPU. This enables also GPU oversubscription, that is the capabilities to use on the hardware accelerator memory regions that are bigger than the on-device memory one. But there is a problem. Here I'm showing to you Black-Scholes, which is a financial market simulation. It is a benchmark that is massively parallel, and it is executed on two NVIDIA server-grade GPUs with 16 gigabytes of RAM in each one of them for a 32 gigabytes total. As you can see, as soon as you start processing 8, 16, 32 gigabytes, you start to experience a linear execution time. So you process double the data, you take double the time. But as soon as we reach 64, something happens. It changes the behavior of the whole benchmarks. And what changes is the fact that you are effectively using unified virtual memory over subscription. That is, you're using more memory than the one that you have on your hardware accelerator. So what can you do? There are two main approaches to solve this problem. The first one is to hand-tune the behavior of this unified virtual memory. So to issue some calls to the runtime in order to fine-tune and optimize each data movement. This is unfortunately workload specific, so you need to change and to do this characterization for each of your different workloads. And moreover, this needs to be done for different dataset sizes. So each time you change your dataset, it might happen that the performance that you obtained before is not there anymore. The other option is, of course, I can scale out my solution. So I'm using more memory than the one that I have on my hardware accelerators. I use more hardware accelerators. Unfortunately, to obtain this, you have to restructure your application to match predefined programming models, such as CUDA-aware MPI, Nickel, or NVIDIA Share Memory. There are many more technologies, but you need to change your application. So GROut fits in the middle. So it enables you to hand-tune unified virtual memory transparently and to scale out your solution, again, transparently. It has been developed in collaboration with Oracle Labs, and it uses GraalVM, which is a Java virtual machine that is polyglot. So it enables you to use multiple programming languages, such as JavaScript, Python. You don't have to be bound to C, C++. And the goal of this project is to require a minimal expertise from the user in order to use the overall framework. So let's see a very, very brief example of a program. This is the Python APIs of GROut, and in particular, you just need to import the polyglot capabilities, and then you can build your kernels at runtime or use pre-compiled kernels in your pipeline, kernels that you have already there, and kernels are just the application that are running on your hardware accelerators. You need to allocate, given the fact that we are a library, you need to allocate memory regions within our library, so you need to pass through us. But then you can use your hardware accelerators as a normal execution flow. So you can initialize those memory regions, start a kernel as a normal function call, and then print the results. And this is a very simple example where you don't have interdependencies between the kernels, but you can have many different kernels with interdependencies between data, input data, and output data. And this will be automatically handled by the framework, so all the synchronization is happening under the hood, and the user doesn't see that this is executing on a distributed system. This is one slide where I will focus the entire 2 minutes that I have. So GROut versus a single node execution. So a single node is executing its normal pipeline, and it's becoming oversubscribed. On the x-axis, you have the different oversubscription factors, where 2x means that I am using 2 times the available memory that I have on my hardware accelerator. And we tested different benchmarks, a machine learning ensemble model, conjugate gradient, and matrix vector product. There are some benchmarks used to perform this characterization. On the left part of the axis, you see the normal behavior. We are not oversubscribed. We are not using unified virtual memory oversubscription. On the right side, we are using oversubscription, and as the baseline, we are plotting the single node execution, while the actual result that you're seeing is G out on 2 nodes. So one could expect a 2x of performance improvement, but given the fact that we are using the oversubscription, we reach 7x and 24x of performance improvement on the overall workload end-to-end, considering all of the additional overhead of going distributed. So this is a wrap-up of what GROut brings. It brings a massive reduction of line of code and the complexity for the programmer, where all of the synchronization, data movement manually are hidden from the user. It reduces the impact of unified virtual memory over subscription by providing a transparent workload distribution free for the user, and the user doesn't have to interact with a distributed system. So thank you for your attention, and if you have any question, please drop me an email or you will find myself there. Thank you very much.